So I'm very happy to be here. Many thanks for the organizers for doing this. I have excuses to make. First, I don't know so much about Robin, and I'll make it even worse by pretending nothing was known before us. That's not true, but that saves 5 minutes, and I'm ignorant anyway. I still wish to thank Marcel Filoche, which is this indirect way of saying nice things about Bernard Sapoval. He was the one to convince us that the Robin problem was actually interesting, right? Before that, I was a pure mathematician, so I said, well, Robin is between Dirichlet and Neumann. One additional parameter, what do we care? Okay, so anyway, I'll try to talk a little bit about that a little later. So the team is with Svelena May-Broda, whom I've been working with on many things for a few years now. Max Engelstein from Minneapolis, who's also a little bit like this. And then we have two nice postdocs, Stefano and Marco, who are one with a mixture of Max and Svetlana. Okay. So anyway, and thanks to Marcel, we essentially discovered what Robin is about. Okay. So this is the definition of Robin. Let's say I'll call it Robin problem. You could use other elliptic operators than the Laplacian, but for today the Laplacian is fine. So you solve the Laplacian equals 0 inside. Okay, and then there is this strange Robin. It's also called Fourier from time to time. Boundary condition, which is that you take the normal derivative of u multiplied by some coefficient. We decided it's 1 over a. Then you add the function itself, and either you get either you ask that it is 0 locally, or you ask that it's a given function f, depending on what you want to do. Okay. So here we'll not complicate our lives too much. Omega will be a nice domain for the moment in Rn. We'll discuss how nice it is along the way, following the great tradition. I orient the thing so that when my function is positive and increases, the normal derivative is positive too, right? So, okay. There are limiting cases. When a tends to 0, you tend to a Neumann boundary condition, which means du dn is equal to 0. I'll say 2 words about it very soon. And when a tends to infinity, you tend to the Dirichlet conditions, which is the ones that have been most studied in this case, okay? And unfortunately, I cannot compute so many Robin solutions, but at least I give you two. One, which is t plus 1 on the upper half space, okay, which satisfies this condition, okay. So t alone would be Dirichlet, and t plus 1 allows you Robin. And the second one is a version of this on a ball, and let's say in this case I used the log, so it means that the dimension is 2, and I explicit function, and it is again something like 1 on the boundary and has normal derivative 1 on the boundary. Yes? So I do not want to think about whether it's inwards or outwards, but let's say in the upper half plane, the again du dn, when u is increasing, du dn is positive, so it's inwards. So in fact, I did the thing that I would claim that I claimed I would never do, but okay, right? Okay, good. Okay, so this is the way to have nice. I mean, half of the time you study about positive solutions, and it's more convenient this way. Okay, so 2 examples. Again, you could do other elliptic operators. That's not the point today. Let's spare this. Then there is the notion of harmonic measure, and again, you're supposed to do something which is pretty much like a harmonic measure in the Dirichlet case. So one way to say it is that the harmonic measure, which I call omega Robin at x of a set E, is the solution of this problem, where you ask again Laplacian equals 0 in the domain, and you ask for the boundary, the Robin boundary condition to be equal to the characteristic function of the set in the boundary. All right, and in 2 minutes I'll try to explain about random walks and things like this. But for the moment, it's the definition. And another way of saying this is that it is the function that allows you to compute the solution of a previous problem. The previous problem was the thing here with function f. And the way you get it is by integrating the harmonic measure against f, okay? As usual, okay? The only, yes, something wrong?
So the equation for, you have a log A,
you mean the first equation too?
No A.
Hmm? Ah, so I forgot the A somewhere. No? No. There is Robin A of U F. It's my way of saying 1 over A du dn plus U, okay? And I try to contract it into saying Robin, so that this way, for instance, a simple solution would be Robin equals 0 instead of being U is equal to 0. And I'm looking at this strange condition. And again, if you're used to Dirichlet, it's something slightly unpleasant. The function U is not 0 on the boundary. It is usually positive, say, if you want the function U to be positive everywhere. And it's increasing a little bit more, okay? And then Neumann, I'll discuss in a few seconds. Yes?
So maybe the question was, does this measure also depend on A?
So A for me is fixed, it's a constant, and of course it depends on A, okay? And the question is, what sort of behavior are we supposed to expect? And again, I'll try to be away from Dirichlet, which we claim we know, Neumann, which people usually don't consider, and I'll explain why in a few seconds.
The outward or the inward? No.
So I think it's inward. I think we decided it's inward, but again, don't pay attention. The signs are working fine at the end if you if you choose the correct definition, and I don't think you want to spend your time doing this, okay? And again, at the end of the integration by parts, you have to trust me. Right. Okay. And myself, I trust other people. Okay. So Brownian motion, so it's just a vague idea, but it's still good to know. So for Dirichlet, the way you think about it is you start a Brownian motion from the pole, and then eventually it hits the boundary, and the probability of hitting on the set E is harmonic measure of E, okay? Here it's something the same type, but you imagine that the Brownian motion is reflected along the boundary with some probability to bounce. And when I'm saying bouncing, I just mean, it goes there and it starts again. I mean, no, don't imagine reflections where you just do like a tennis ball. You just restart again. And the notion is complicated because you shouldn't restart again infinitely many times because the Brownian motion, it starts from the boundary. It's very likely that it's returning to the boundary almost immediately. So it would be easier if you were thinking about a random walk, and then for a random walk, you would hit the boundary with probability alpha related to A, you bounce. With probability 1 minus alpha, you stay and you count this. Okay. And again, it's good for us. I mean, we're never going to use this because if you wanted to use this, we probably would have to learn more about the local time in complicated domains. And I made the right move. I went to ask Jean-François Le Gall, oh, what about the local time on a rough domain? And he said, Some people have studied it, but I don't trust that. Okay, but it's good to think about it anyway, right? As a vague thing. Okay, reflecting. What I should say again in about Marcel Filoche. So apparently this is the correct way of let's say, physics or anything applied, because you do not imagine that Brownian motion or something like this will automatically be absorbed. Okay, and he has his one main example, which is the lung. And in the lung, apparently, this is exactly what happens, right? The particles come in the lung, and maybe they attach and they give you oxygen, but more likely not the first time. They bounce back, they go a little bit further, and so on and so forth. Okay, and so that's if you want a description of what happens in the deep part of the lung, Robin is the right one. Okay, good. And but it could be more or less the same thing, right? You have you think about heat in a room, and then you could say, you could put some Dirichlet or Neumann condition on the room, like Neumann, which is, the thing is perfectly insulated, but it's not perfectly insulated, right? Okay. And this is the reason why the thing is also called Fourier, because he was interested in what happens with heat transfers also. Okay, so that's the name. And the main question is, since we know a lot about the Dirichlet harmonic measure, what can we say about the Robin harmonic measure? Does it behave the same way? What's going on? Okay. No more questions? Okay, good. So I have to give you a rapid review of what's happening for the Dirichlet thing, because otherwise you're going to be disappointed with Robin, right? So Dirichlet, I'm supposed to say that the situation is fairly complicated. It's better and better understood now. It's, some people could say it's almost completely understood, at least to some extent. But anyway, I'm supposed to tell you the situation is complicated. I also like to make history start with Dalberg. Before that it started, but it was a story of conformal mappings, so you could say it's cheating a little bit. So in many dimensions, Dalberg says harmonic measure is absolutely continuous with respect to surface measure on Lipschitz graphs. And then the story continued about, what is the correct notion to replace Lipschitz graphs. And at the end of the story, the correct notion is something like uniform rectifiability. Also, you need this domain to be connected in a sort of a uniform way, because of course, if the domain is cut into two pieces, harmonic measure starting the Brownian path here will not talk to the rest, okay? So you need some connectedness. And again, the reasonable notion of connectedness is what's called non-tangential access or uniform domains. It's the same as this morning, and it's, okay, it's sort of well understood. It's complicated, but it's well understood. Okay, and that's essentially the situation for Dirichlet, all right? I add some more comments. Here, for instance, you could ask what's happening with the Cantor set of dimension 1 that you saw this morning. Okay, let's imagine your typical Cantor set and you make it of dimension 1 by choosing 1/4 when you cut things into pieces. And it's been well known that this is a bad set for harmonic measure. Okay, so harmonic measure in this case is supported on a strictly smaller set, okay, a set of 0 measure. Two things are orthogonal, the two measures are foreign to each other, okay? So that's supposed to be a bad case, okay? You can also ask the same sort of questions in different dimensions, and typically when you're trying a set of dimension strictly less than, let's start strictly more than n-1, you know that harmonic measure will live on a subset of dimension. Let's say you're in the plane of dimension 1. So it's really going to be living on a very small set. And even on fractal sets of low dimensions, like my Cantor set, but make it of dimension even lower, harmonic measure will be living on a set which is strictly smaller in terms of dimension. Okay, so that's what happens in general. And I make a last comment. This is in general for the Laplacian, okay? Then there is another piece of theory which I spare you, which is, can you replace the Laplacian by some other operators, other elliptic operators? And typically if you take any other elliptic operator, things will not work well, okay? There are counterexamples where absolutely continuous. So for instance, Dalberg's theorem becomes wrong. It stays right if the operator is close enough to Laplacian or constant coefficient operator, okay? And there are conditions that say how close it has to be, and then you have absolute continuity and so on and so forth. And I probably mentioned somewhere in the slide that there are these strange examples, like, for instance, there is a possibility to put an elliptic operator on the counter set so that harmonic measure is equivalent to Hausdorff measure. But that's when you do it on purpose, right? The general situation should not be like this. Okay, so that's what I claim is the situation for Dirichlet, and again, complicated situation, but well understood. Okay, and you can start asking what happens with Robin, right? So the typical sort of questions that I was asked was, for instance, is there a phase transition when you change A? Does something strange happen in terms of, you know, what's happening to the Robin, the support of the Robin measure, and so on and so forth. Okay, I don't answer immediately, but yeah. I gave a partial answer because I said that the thing might look disappointing. Okay. Now, in order to define things correctly, so everything that I'm going to say is well defined and reasonably, you know, it's easier to understand when you're talking about a set of whose boundary is of dimension n-1. But at the same time, you know, the conference forces me to study fractal sets, and I'm very happy about this because this is what I intended to do anyway. So there will be, let's say, a possible second part of the domain where I'm looking at sets of boundary of dimension different from n-1, like fractals. I mean, all the, what's happening? I know the second part is, yeah, no, you know, I was worried, but I was already finished. What would have been mean? Okay. So anyway, other sets of other dimensions, like this morning's fractals. Okay. Good. Now, 2 words about Robin, about Neumann. Usually people don't look at so much at Neumann. I mean, we were trying to look for the basic results for the Neumann boundary conditions, and we essentially couldn't find them, and there is one good reason. You know, for instance, people like Lipschitz domains. On a Lipschitz domain, there is a reflection from the domain to the complement, and the reflection amounts to changing the elliptic operator a tiny bit, and then the Neumann condition is such that when you reflect, you can reflect a Neumann solution into a solution global, which means that usually people say Neumann is easy because you do reflection and you look at inside boundary, inside regularity, and that's it, okay? I'm coming a little bit more from the calculus of variation, and again, for the calculus of variation, Neumann is a pleasant situation because essentially for me, Neumann condition at the boundary means no condition at the boundary. You let the function U do what it likes, and you minimize this energy, which is always the same integral of grad U squared. I don't know where it is. Yeah, up there, okay. Okay. And we'll see that, for instance, for simple domains, the Neumann harmonic measure is just normalized surface measure of E. Okay, so it's not supposed to be very interesting. Okay. Okay, good. One thing I like about Robin is that it can be made into minimizing functionals more easily than with Dirichlet. Okay, so let me say 2 words about this. Let me write down a formula, which is this function. Whoops. I thought I would be the only one that would not do that. Okay, so here is this functional. Okay, E of U is this energy that I use all the time, integral of grad U squared. Okay, and then I try to minimize the functional with 3 terms. One which is energy divided by A. The second one is integral of U squared at the boundary. Okay, again, d sigma, and now d sigma is just surface measure. And the third one is the one that depends on E, which is you just subtract 2 times the integral of U, not U squared, on the boundary. Okay, it's not so hard to show that this functional has minimizers. Essentially, it's convex and bounded from below, so it's not, you know, it's not deep. So you can look for a minimizer if it's functional, and this minimizer has a certain number of properties. The first one is that in the bulk, you're minimizing integral of grad U squared, so you get harmonic function. Okay. Once you know its harmonic function, you can try to compute the energy, and the energy is computed somewhere here, integral of u du dn, okay? For the moment I'm saying this. Now, if you have a minimizer of this thing, it means that you can try to use the Lagrange multipliers or whatever it is. Anyway, you take u plus t times some other function, you expand in t, and you get that the derivative in t is equal to 0 at the origin, and you get some equation. Okay, so that's what I call by Lagrange multiplier. And you find out that the Robin condition is exactly the condition that you need to minimize this functional. Okay, let me say it backwards. If you want to compute the harmonic measure, you compute this function ue, which minimizes the functional. Okay, and the value of ue at the point x, which was your pole, is exactly harmonic measure that you wanted to compute. Okay, so in principle, if you want to compute harmonic measure, contrary to what happens with Dirichlet, you just minimize this functional, which is a nice functional, and compute the value at the pole, and here is your harmonic measure. Okay, so if you were trying to do this with Dirichlet, you would still minimize this energy E of u, but the constraint would be that u is equal to 0 at the boundary. And boundary constraints, they're supposed to be a little harder to tackle because you have to know, it's saturated, as people say, and how do you use this information that u is equal to the boundary, so you're on the boundary. It sounds like it's a beautiful condition to everyone, but it's hard to use, okay? And here what happens is the function u is free to do whatever it likes at the boundary. It's just that when it's large, you have a price to pay. Okay, and the price to pay is the integral of u squared up there. Okay, so anyway, minimize, for the moment, I'm saying, nice functional, you can minimize things, okay. And for instance, the second thing is that for Neumann, it's very easy, so now I have to rush a little bit, but it's very easy to see that the minimizer should be a constant, and you can compute the constant and you get whatever it was. Okay, good. Okay, current assumptions. So I try to go a little bit faster because you heard about these assumptions. For the moment, or let's say what's written in the paper, which is circulating so far, is alphas regular of dimension n-1, okay? Uniform connectedness of the domain, so NTA condition on the domain, so that you have nice connectedness. And A is any operator which is elliptic and symmetric. Symmetric, I'm not completely sure it's needed, but since I like to do variational arguments, it's better to take it symmetric. And it could be that it's really needed. Okay, but what I really think about, because this is a fractal conference, is you can replace alphas regular of dimension n-1 by alphas regular of any dimension which is reasonable, and which means the boundary is any of the d sets that you saw this morning. Okay, good. And we have a theorem. So this is the disappointing theorem. For any a different from infinity and 0, a harmonic measure with a Robin type is absolutely continuous with respect to surface measure. Okay, so nothing special. It stays so even with elliptic operator which were supposed to be bad, which mean, even if you're far from the Laplacian, you're still okay. Okay, and essentially no other condition than what I said before. Okay, and the two things are harmonic, are absolutely continuous with respect to each other. And okay, so this is the basic statement, right? Nothing bad happens. No completely obvious change. So the set is, the boundary is alphas regular. And where do you say? And then I'm saying first, there is an existence and unique Ness theorem on which I go very fast, okay? Then there is the usual elliptic theory that you can do in those cases, which essentially means Moser and regulating.
My question, the real condition.
It's okay?
Yeah,
more or less?
Huh?
Don't hesitate, right? Yeah.
One condition I didn't say, but it's okay.
Okay. So anyway, so the theorem number one, which I even don't say, is all those things that I've been talking about are well defined, including harmonic measure. Okay. And harmonic measure, you had two solutions. You had two definitions. One as a solution of a variational problem, another one as a solution at the beginning, and those two things exist. And again, the main new thing is mutual absolute continuity of surface measure, and it will become Hausdorff measure as soon as we improve the written statement, and harmonic measure. Okay? Good? Okay, so that's the statement. Let me try to go, okay, so this is the story to say that there are general things. This is the story to say whenever I announce a statement saying two measures are absolutely continuous with respect to each other, in fact, I typically mean there is an A infinity condition that goes from one to the other. And at the way it is written now, it's not a beautiful A infinity thing, because there are constants, there is this quantity AR that shows up in one place too much compared to what it should be. It should be that when you're close to Neumann, situation is getting better and better. And we don't have this in the statement, and we'll hope to improve very fast. Okay? So don't read that story, just, okay. This statement is quantitative in some ways, which is essentially the same way as usual, okay? And I try to convince you that the statement is easy, so I'll do the thing which is extremely easy, which is just try to prove that the two measures are absolutely continuous with respect to each other, okay? And this I can do in one slide. So again, remember, harmonic measure is just given by this functional that you minimize. So you call UE the minimizer, and you want to know whether measure 0 on one side implies measure 0 on the other side, okay? And I try to start with the first thing. Suppose surface measure is 0. If you look at surface measure 0, then of course, of E, right? It means that the third term, the thing that is negative, is 0. Can you do better than the 0 function? No, the functional is positive everywhere. The best solution is U is equal to 0. So UE is equal to 0, you compute it at the pole and you get 0, okay? So that's one way. It says that harmonic measure is 0 when surface measure is 0. In the other direction, it's not much more clever. Suppose harmonic measure is 0, you have a Harnack principle, those things are positive harmonic measures, positive harmonic functions. So you get that UE is 0 all over the place, which means the infimum of a functional is 0. And if the infimum of a function is 0, and also I told you there's a unique minimizer, this is one way of cheating, well, you find out that, there is a simple way to make this thing here, the -2 terms here, larger than the other ones by taking U small enough and taking a bump function. And so anyway, what I'm saying is that if sigma of E is different from 0, it is not possible that the infimum is positive. It is strictly negative because you can compute. Okay. Right. After this, so what I'm missing is true estimates, but you get an idea. I hope I convince you of at least one thing, which is putting variational calculus in this business is simplifying things enormously. To say it, you know, we are in a situation where we can put variational inequalities in this, and then you simplify your life a lot. The second thing that I didn't say, and I say that in 10 seconds, is the important thing to me is the fractal piece that I did not talk about at this time. I'll possibly zoom to the place where there's a weak definition. So this, okay, weak definition. So you might be disturbed by the fact that I'm talking about normal derivative of a function at a boundary which is fractal, okay? And at the same time, maybe you guys are not so much worried as some other people. And the main point is that, of course, you want to define the normal derivative in a weak way, okay? And here I wrote the way you write. So equation 9 is the one we had at the beginning. Equation 10 is the way you translate it into a weak way. And it makes sense, and you see what happens is that you have to be able to integrate against a surface measure, Hausdorff measure of dimension d, and you want to make sure that there is a trace of functions in the energy space. So if you have a function in W1, 2, you want to make sure that it has boundary values which are at least in L2 of sigma, okay? And then you can start the game. And the beginning of the game consists in having sufficiently many Poincaré inequalities so that you can build a good trace. And afterwards, afterwards it's not so hard. But for me, the main point is one of these, right? It's, you don't want to restrict yourself to sets of codimension 1 because this is the natural setup, okay? Okay, thanks. Sorry.
Many thanks for this very clear and inspiring talk. Are there questions? Oh, where I start? Maybe I start upstairs and then work downstairs.
So, do you have any continuity with respect to A? The measure?
I think, okay, so some continuity, yes. So for instance, when you solve the problem and you let A vary, there is one thing which is the solution, for instance, the solution UE is monotone, depending on E, on A, which is a very good sign, right? So afterwards, I think there are other things to prove that we didn't do. And one of the typical ingredients of the things to prove would be to be able to say either we change A a little bit or we change the domain a little bit, try to see what happens to the solution. And for the moment, I'm saying those things should exist. Okay, but they're not written, but they should exist. But already monotonicity is really, it's a hint that nothing will go wrong too bad. We also have expansions near the Neumann end. So with Neumann end, we can say that Robin is the sum of a geometric series of iterated solutions of du dn is equal to given something, okay? So some things exist, okay? Which is my reason why I'm saying, I don't believe in this, radical change in terms of u. I think what happens when A tends to infinity, which is the bad thing, estimates get worse and worse, and at the end you get what you know for Dirichlet, right?
So how essential was that your choice of the boundary measure? So you choose the boundary measure sigma to be the Hausdorff regular measure on the boundary, yes, right? But typically, it seems to me that it could be replaced by some other measure on the boundary.
Sure. Okay. Good.
Then,
yes.
Do the things work in the same way, or?
So I think the correct. So there's one thing that I didn't say. If you multiply sigma or divide sigma by some number, or if you multiply it by a function which is between 1 and 2, it's amusing because you seem to be solving a Robin problem with varying coefficients, but it's completely hidden in the sigma. So that's the reason why, for me, A was a constant, because I can hide small variations in sigma. Now, your question you ask, I think, so let's say I have my answer to the question you ask. I don't know if it's the correct one, which is that, in fact, nothing forces the set to be Alphorst regular of some given dimension. The main thing is that there should be a doubling measure on the boundary. The doubling constant should not be too large or too small, because we have this condition that the set is morally Alphorst regular of some dimension, which is strictly between the two important ones. So the doubling constant is not allowed to be anything, and normally things should work. And we're saying this because we did something similar for the Dirichlet problem with variable dimensional boundaries, and we expect the same condition to work again, okay? And I think that's probably general enough for you then. Okay.
Thanks.
No, I'm thank you, yeah. Good, yeah.
So your solution U, of course, is a landscape function for the eigenfunctions of the Dirichlet to Neumann operator. Do you have any information about the accuracy of how well these eigenfunctions are approximated dependence of the roughness or the smoothness of the boundary?
So the short answer is no. I think our guy is not a landscape function because you would integrate. Let's say if you take an average of a green function, you would take something that looks more like a landscape function to me. But and otherwise, I don't know. Yeah, I don't know for sure. Again, we're going in the track of saying, we have these functions, they have some regularity, we understand this regularity. But for instance, the typical thing that we don't know how to do, because we don't even know it in the standard cases, is suppose the normal derivative is some L2 function. What can we say about the maximal function of a gradient squared? This is too hard for me. Some of my colleagues are trying very hard, but that's a different story. Otherwise, we discussed because I'm not sure I understood the question. Yeah.
Can you also add a potential to the Laplacian so that you have minus the Laplacian plus a potential? And
so I think, we didn't look. Of course, I would advise to say, cut it in two. You write down, you integrate the risk potential against your second member, right? And again, when I'm saying potential, you mean potential applied to U, and then we absolutely didn't look. If you're thinking about just Laplacian U is equal to some given function, you can try to use the risk kernel to compute something, subtract, reduce to the previous problem, and I don't know. And in your Schrödinger case, we didn't look. But of course, the way I would start is to say, the Schrödinger part, I put it on the other side, and I try to say some reasonable things, okay?
So are you also using maximum principle, so the potential has then to be positive, or can it also be negative?
Sorry?
So is it, do you need maximum principle things and techniques?
So we have a maximum principle here. It's okay. And again, we don't do systems. We don't even do non-symmetric.
Maybe one last question then?
Yeah.
Okay, just a remark. It reminds me also of a classical problem, which is the boundary layer, which appears in hydrodynamics, in wave equation, and so on. If you introduce, let's say, U minus the Laplacian of U, and then you put a nu in front of the Laplacian, and you let the nu go to 0. In this case, you will have a boundary layer near the boundary, and the boundary layer is much stronger with Dirichlet than with Robin.
Okay.
And I wonder what's happened if you play with these extra parameters in a region of
Okay.
that type.
Never thought about it. Good suggestion. Thanks.
Many thanks for
I don't know
questions.
more. Yeah.
Please let us thank the speaker again.
Okay.